My name is Raksha Khan, and this is my Physics 2 lab report for Lab 4 on circuits and capacitors. So the goal of this lab is to predict and determine the current and potential difference in different circuits using ammeters and voltmeters. For this lab, the fundamental physics principles that we'll be applying are the loop rule, also known as Kirchhoff's voltage law, and the node rule, also known as Kirchhoff's current law, and both of Kirchhoff's laws are given over here on the left. Kirchhoff's current law says that the sum of the currents at the node is equal to zero, so the current going into the node is equal to the current going out of it. And Kirchhoff's voltage law says that the change in voltage over in the circuit is zero. As well as Ohm's law, and the formula is given over here on the left below Kirchhoff's law, and a general understanding of capacitance and currents in series and parallel circuits. So first of all, based on our prediction, we can use Ohm's law, and then substituting the values for voltage and current and resistance, we can solve for current, and we get a value, and then applying node rule saying that the current in the first ammeter is equal to the second, we get that it's 0.02 amps, and this is the correct prediction when we model it using the FET simulation, and the answer is negative if we flip the ammeter because the current will go into the negative terminal. And then if we replace one of the ammeters with a voltmeter, the ammeter would read 0 because the circuit is open, so current can't flow, whereas the voltmeter would read negative 3 volts because we're adding the voltage of the two batteries that are each 1.5 volts. And then the potential differences when we map it out at different points from A to B, B to C, and so on are given over here on the top right, and the sum of them would be 0 volts as we know from Kirchhoff's law, and here's just a graph showing how the different potential differences between different points. And if our ammeter was in a parallel circuit, then the ammeter would still read 0.06 amps because of the node rule, and the ammeter has no resistance because it's zero, so zero, and then all current would pass through the ammeter route and none would go through the 100 ohm resistor route, and because of that, current only interacts with the 47 ohm resistor. And then to find the resistance at different points, we can use Ohm's law again, voltage divided by the current, and so we just substitute the values and we get the following results given here on the right. And then for charging and discharging a capacitor, when charging, which is over here on the left image, the bulb lights up brightly and current flows at max capacity. At t more than 0, the bulb dims and the current decreases, which means it slows down. And then t much more than 0, the bulb turns off because the current stops flowing. And discharging, basically the same thing happens. The only difference is that the current is reversed when discharging. And the image for discharging in the simulation is the one on the right. And then for our RC circuits, we did it 20 different times to get different values, and then we plotted it in the graph. First of all, the time to charge or discharge the 20 ohm bulb was approximately double that for 10 ohm bulb, and so we can see that there's a clear relationship between resistance and time. And we know that the slope is we can find the RC value by knowing that the slope is equal to -1 over RC, and so we plug our slope value of -0.1448, and we get RC value of 6.906 seconds, which is pretty close to our expected value of 6 seconds. And then finally answering some conclusion questions. So actual ammeters don't have zero resistance. So only the ideal ammeter had zero resistance. So because of that, the actual current would be lower because of the resistance. And the model charges the capacitor much faster than it would in real life because it ignores internal resistance because of the wires and such. whereas in real life there would be internal resistance, and so it would take much more longer to charge. And that's it for my lab report. Thank you.